Thanks everybody for coming out to my talk. My name's Michael Becker. I work on the Data Ninjas team at Aweber. Aweber is an email service provider located just outside of Philadelphia. And I'm also the founder of the Data Philly meetup, and we have over 800 members. So, working on the DAM team at Aweber, I've introduced several predictive algorithms into our application, and my coworkers think that I'm some sort of math superhero, reading scholarly papers by day and fighting crime by night. But the truth is much more sinister. So fortunately for me, I don't have to be a genius to look like a superhero. I just have to use Python. While I'll cover some math in this talk, I'll mainly just be keeping things high level. Okay, so what will I be covering today? So to start off, I'll define what is data science. I'll teach you the OSEMN data science process. I'll demonstrate how to create a custom web scraping bot. I'll convert the data to plain text. I'll explore the data using pandas, seaborn, and scikit-learn. And finally, I'll walk you through creating a predictive model using scikit-learn. So what is data science? There's a lot of disagreement on the subject, but I like this Venn diagram that was created by Drew Conway, which gives us a good high-level overview of what skills are involved in data science. So Conway argues that at a minimum, you need these three main skills to be a good data scientist: hacking skills, math and statistics, and substantive expertise. So in the hacking circle over here, he includes things like manipulating text files at the command line and thinking algorithmically. In the math and statistics section, I think is pretty straightforward. You need to know math and probably statistics. But Drew argues that these two on their own are not enough, that you also need to understand your data. You need domain knowledge and expertise. So I'm not sure if it was Hilary Mason who first coined the term OSEMN, but that's certainly who I learned it from. OSEMN is a typical data science process followed by many data scientists. So let's break it down. Obtain is pretty straightforward. To do data science, you first need data. Not all data is going to be easy to access, so be prepared to jump through some hoops to obtain your data set. Okay, so you have your data set. Now what? If you're lucky, your data will be well structured and easily parsable. But in reality, it's rarely that simple. Messy data is the norm, not the exception, but don't panic. Scrubbing your data is just another part of the job. To get the most out of your data set, you need to understand it. This is where the explore step comes in. This can be as simple as looking at your raw data in a text editor, or as advanced as running machine learning algorithms on your data. Sometimes you want to predict the future using your data. This is usually where machine learning comes into the picture. So the goal here is to maximize your predictive power by minimizing the level of error. And a model isn't useful on its own. And so this is where the interpret step comes in. Often while interpreting the results of your model, you'll identify areas for improvement which will allow you to iterate and improve on it. So even a bad model can lead to some useful insights. So in this talk, I'm going to walk you through the OSEMN process by building a language classification algorithm from scratch. A language classification algorithm will predict the language of some text. So for example, if you might give it the text yada, 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 and it would classify this as English, presumably. So language classification can be useful on its own. For example, I've actually used this algorithm that I'm going to be presenting to you guys today to break down Aweber's customers by the language that they use in the emails that they send. And it can also be a useful pre-processing step. So for example, Google likely uses it to automatically detect what language that you're typing into Google Translate, and Google Chrome probably uses it to detect the language of the web pages you're viewing. So step one of the OSEMN process is to obtain the data. In the case of our language classification model, we need text in a bunch of different languages. Fortunately, Wikipedia has an abundant supply of this data. There are Wikipedia datasets available online, but that's not much fun. Let's build our own. So to start off, I grabbed a list of hourly page views from this the dumps.wikimedia.org, and I wrote some scripts to aggregate this data for several months, and then I compiled a list of the top articles per language. Next, I used the special export page for each Wikipedia to export the pages that I want. And this task was made trivially scriptable via the use of the copy as curl command in the Chrome developer tools. And then I also found this other awesome library called uncurl. And so you give it like the output of the copy as curl, and it turns it into a Python request module code. So this is, you can literally run this code and it will make the same curl request. And then you make some minor modifications to it to like parameterize some of the things, and you have an instant Python bot. All right, so now that we've obtained our data, the second step is to scrub it. The dumps from Wikipedia are in XML format, so we'll need to pull the articles out of the XML. Luckily, I didn't really have to write any code for this. There's some Python code that already does this called Wikipedia extractor. And it produces output that looks like XML, but it's not actually XML. So I spent some time trying to figure out if I could fix the code, but it was a bit ugly. So rather than trying to fix their code, I just wrote a simple regular expression to parse out the data that I needed. All right, so our data's scrubbed. Now it's time to explore. To start off, I counted the number of times each character occurs in each language. And then I grabbed the top 2,000 from each of them. So after I ran this code, I have a list of dictionaries that makes it easy to load into a pandas data frame. And you can think of a data frame as a mix between an Excel spreadsheet and a SQL database, but it's Python. So the first thing I did once I loaded it into a pandas data frame was I calculated the percentages from our raw letter counts. So we can do this using the div method. And then we can add these percentages as columns to a new data frame by using the join method. And if you're using pandas inside of IPython Notebook, you can get you can easily display the contents for inspection. All right, so now let's use two unsupervised machine learning techniques to visualize our data. There's a lot going on here, so let's break it down a little bit. First, we run the k-means clustering algorithm on our letter percentages. And what k-means does is it automatically groups your data together based on similarity. Next, we run an algorithm called principal component analysis. And we're using PCA here to reduce our number of columns from 10,000 to 2. And the reason for this will become clear in the next slide. Finally, we plot the results. And since our data only has 2 dimensions, since we ran PCA on it, it's really easy to plot. And in this scatter plot here, the color of each point corresponds to the cluster that it's in. And we can see that with 4 clusters, there's a pretty clear separation. Like, for example, like I could draw a line here, and it's pretty obvious that these all are going to be on this side, and these are all going to be on that side. And for each of these, it's pretty easy to draw just a line to separate them. But one thing I noticed right away was that when I got the data like this, there's some clear outliers. So I dug into the data a little bit, and basically what I found was that most of these languages use their own unique character sets, which is why they're way out here in nowhere's land. All right, another way that we can kind of dig into this data is we can use the pairwise distances function from scikit-learn, and we can use that to find the languages that are most similar. So this function, pairwise distances, calculates the Euclidean distance between each pair of points. The smaller the distance, the more similar the data points are. So we can see that the most similar languages are in our first cluster, cluster 0. And Croatian, Serbo-Croatian, and Bosnian are the most similar, followed by Indonesian and Malay, Danish and Norwegian, and English and Scots. Some of these really similar languages will probably be useful for us later on when we're training a classifier to help benchmark it. Finally, seaborn, which is a graphene library that's built on top of matplotlib, is really awesome. It has a bunch of really awesome graphs built in, and they're really easy to use. And so we can use some of these graphs to visualize the similarity of our languages. Here we have what's called a violin plot, and it's similar to a box plot if you've ever seen them, but basically you get the distribution of the letter frequencies in addition to the 25th, 50th, and 75th percentiles. So here we can see, like, for example, that Arabic and Egyptian Arabic are really similar. So Seaborn also has a ton of other awesome graphs built in, and here's just a few other examples. They actually released a new version yesterday, I think, and I saw that they added some cool cartography-based plots, and there's some stuff with heat maps. Anyway, check out their docs. They have a lot of really cool stuff. All right, so now that we've finished exploring our data, it's time to build our model. Our model is what's called a supervised model. So let's start off by defining what a supervised model is. So you start off with some input. In this case, we have our Wikipedia articles as our input. And we call this our training set. So you also have some labels for each piece of training data. And in our case, our labels are the languages. So you might note how this differs from the k-means and the PCA algorithms that we ran before. They didn't use labels, and that's the difference between supervised and unsupervised learning. Next, you convert your data to a numerical form. Then you train your machine learning algorithm using your vectorized training data, and the labels as input. So this is often referred to as fitting your model. And at this point, you have a model that you can take a new piece of unlabeled data and predict the label. All right, so let's see how this works in practice. We call this type of algorithm a classifier because you provide some input and it classifies it as one of multiple classes. In the case of our algorithm, you provide some text as input and it will classify the language of the text. To start off, I've defined a pipeline which combines a TF-IDF vectorizer with an SVC classifier. And a pipeline is just a utility that allows you to build like a multi-step classifier. The vectorizer converts the Wikipedia articles into a numerical form, and it does this by counting all the combinations of n character sequences in our data. And these are called n-grams. And after it does the counts, then it applies another algorithm called TF-IDF. And the pipeline understands how to connect the output of the vectorizer to the input of the SVC algorithm. So SVC is a classification algorithm, and it stands for Support Vector Classifier. And it takes numerical data as input into its fit method. And once fitted, SVC can predict the label of new data points. And again, the pipeline understands how to properly connect the output of our vectorizer to the input of our classifier. So all that's left to do is fit our data on our model. Let's look a little closer at these X-train and Y-train that we're passing in. So X-train, going back to our previous diagram, X-train is the portion of my data that I set aside for training. And it's an array of text from our Wikipedia articles. So besides stripping out the wiki markup, I didn't do anything else to prepare the data. And again, the vectorizer handles converting the text to the numerical form that's required by the SVC algorithm. And Y-train is the labels of our training set. So we start off with this array called Y, and this is a one-dimensional array. And in this case, it contains the language of each article. Unlike X-train, I do need to convert these to a numerical form prior to passing them to the fit method. So we can accomplish this using a label encoder. And label encoder will take our string labels and convert them to numerical categories. So scikit-learn comes with a ton of algorithms built in, and many of them have multiple parameters that you can tweak. And it can be pretty daunting to figure out which algorithm to use and what values to pick for the parameters. So luckily, there's tools built in the scikit-learn to help you tune your model so that you can get the best performance out of it. So one such tool is called randomized search CV. You give randomized search CV a range of values to try for each parameter, and then it randomly chooses some values and tests them. The other cool thing that randomized search CV does for you is it splits your training set into multiple random chunks called folds, and then it uses a random set of these folds for training and another separate set for testing, the trained classifier. And this is what's called cross-validation, and cross-validation helps you ensure that you're accurately measuring the performance of your classifier. So once randomized search has completed, you get the highest scoring classifier along with its score and the parameters. So you can easily run this kind of search on multiple algorithms to figure out which one will perform the best for your particular data set. And now that we have our tuned model, it's time to validate its accuracy. So the metrics module in scikit-learn has several utility functions for measuring classifier performance. Let's go through a few of my favorites. For the purposes of testing the model, I've excluded some data from the training set. Generally speaking, you don't want to train an algorithm using your full data set because many algorithms can suffer from an issue called overfitting. And overfitting is when your model is very good at making predictions about your training set, but when presented with new data, it performs poorly. All the metrics functions I'll show you take two lists as input. The first, yTrue, contains the correct label for each sample in our testing set. And the second, yPred, is the predicted labels for each of our samples. And accuracy is pretty much what it sounds like. It's the overall percentage of correct classifications. So 96% isn't bad, but can we do better? Classification report builds a text report showing the main classification metrics. Ideally, precision, recall, and F1 score should all have a value of 1, with the worst possible value being 0. So, and then the support column tells us how many samples were in our test set from each class. So looking at the classification report, I can see right away that there's something funny going on with, in this case, the Bosnian language. And you might recall from earlier from our explore phase that Bosnian was really similar to a few other languages. So could this be impacting our accuracy? A good way to find patterns in the incorrectly classified data points is to use a confusion matrix. And here's what it looks like for our classifier. Well, that's not really very useful. Let's visualize it. OK, so this is a little bit better. But this is probably hard for you to read. So let's have a closer look at some of the more interesting languages. All right, so how do we interpret this? So you'll notice that each language shows up once on the y-axis and again on the x-axis. And I'm not sure if you guys can read this in the back, but for example, Bosnian is on the first on the y-axis and the first on the x-axis. And so they intersect here. So the y-axis shows the correct label, the true label, and the x-axis shows the predicted label. Anywhere where a prediction is correct, a cell on the diagonal will have its counter incremented. And if the prediction is incorrect, a cell off the diagonal will get its count incremented. So this is a heat map, which means that 100% is represented by the dark red and 0% is the dark blue. So ideally, we should see nothing but dark red along the diagonal, and which would mean that our predictions were 100% correct. And then we'd see dark blue everywhere else. Going along the rows, we can see exactly what each language is being confused for. So in this case, we can see that the languages BS, HR, SH, and SR are often being confused with each other. It turns out that these are Bosnian, Croatian, Serbo-Croatian, and Serbian. And these languages are almost identical, and they used to actually all be called Serbo-Croatian prior to the Yugoslav wars. So this gives us some clues as to how we can improve the performance of our classifier. According to what I've read on Wikipedia, these languages are all the same. So let's just treat them as a single language for the purposes of our language classifier.
I strongly object.
OK. Duly noted.
So the confusion matrix, is that a term you coined?
No. This is a standard. Confusion matrix is a standard technique. I didn't come up with this.
It's a specific type of heat map.
Yes.
Okay.
And so combining the languages that are the same together is pretty straightforward. All we have to do is go back to where we created ytrain, and anywhere where our labels were one of those BS, HR, SH, SR, we just replace them with a new label that we make up. And then we can rerun our random search and retrain our model. So after combining a bunch of these similar languages, we're able to easily get over 99% accuracy. And for some of these languages, if we really wanted to distinguish them from one another, we could try attempting to train more complex models just for them. So like we'd make a prediction using this model, and then if it's one of those languages, then we'd make another prediction using some more complex model. But before devoting too much time into doing something like that, you should ask yourself if it's really worth the effort. And it all comes down to your particular application. All right, so that's all I got. You can all go on your LinkedIn profile and change your titles to data scientist now. A lot of interesting stuff didn't make it into this talk, so I'll be posting some follow-ups on my blog. And if you're interested in receiving some email updates when I post to my blog, feel free to hit me up after the Q&A, and you can sign up for my mailing list. So, any questions? Nothing? Come on, guys.
So all of the data from Wikipedia was UTF-8 originally, or did you have to?
I treated it as UTF-8. I didn't run into any encoding issues, if that's what you're asking.
Okay.
But yeah, I think it's UTF-8. I didn't honestly do a lot of digging there because it just kind of worked. So.
Yeah, because I've seen some people do work where they combine language detection and character encoding detection because they're usually pretty highly correlated with each other.
Sure, sure. So that works really well for languages that like have completely different distributions of character sets, but like for like languages like the ones we were having issues with, like Croatian and Bosnian and things like that, like the frequency is going to be extremely similar, if not like almost identical. So, well, yeah, using just like individual letter frequencies is not going to be enough, and that's why like if you look back way back when I was training the classifier. I actually chose an n-gram range of 2, 3. Actually, this is an older version of my classifier. The current version I'm running, I think I'm just doing 2 grams, which is like combinations of every 2 character sequence. And you're only going to get, I think, something around like 75% accuracy looking at like single characters, for example.
Yeah, I've actually done related work on this where we try to detect the native language of people who've been writing in English, and character n-grams actually work pretty well there.
Oh, cool.
You said this, I'm sure. Why did you want to classify languages?
So in my case, like I was like, oh, classifying languages, that sounds easy, because I like read in a textbook that like all I needed to do was use n-grams, right? So in our case, it was like I had a bunch of text, as I said, like emails that our customers are sending, and we weren't always keeping track of like the headers, the encoding headers that were being sent by their like web clients. So this was like kind of like an easy way for me to get around that issue of not having the data and like figure out like what languages they were actually using.
What does your company do?
We're email service providers, so like we provide like tools for email marketing and stuff like that. So so like people can sign up for our service, and then we provide like some web interface that allows them to like format the emails that they want to send and like collect subscribers and well, SurveyMonkey. I'm not sure like everything that they.
Monkey MailChimp?
Yes. Yep. Yeah. So MailChimp is one of our competitors. Yeah. Yeah, they have a lot of advertising.
Early in your discussion, you showed something I think you called bilingrams.
Yeah.
And I thought it looked great, and I'm sure you can explain to me now. Like, can you give me the for dummies version of what I'm looking at?
Sure. So this is like the distribution of the letter. Do we still have time, by the way? I don't know who's next, but. Oh, really? All right. Oh, I thought I only had a half an hour slot. All right. Cool. So anyway, yeah, so what we're seeing here is the distribution of the letters. I purposely didn't label the y-axis because I had to do something a bit nasty here because, long story short, these don't correspond one-to-one to actual letter frequencies, but in any case, what we're comparing here is this is the distribution of like letter frequencies in this language, and this is the distribution of the letter frequencies in this other language, and you can probably barely see it, but there's like a line here for the 25th percentile, another line here for the 50th percentile, and another line for the 75th percentile. And we can see that, like, for example, these first two, the distributions line up pretty similarly, and the percentiles also line up pretty similarly.
What is the strength of using a violin graph over a box plot?
The advantage is that you actually get the distribution curve. So this curve here is actually the distribution curve.
Okay.
Is that?
Scott, I think I do see the benefit of this
So
for the box compared to the box plot due to the curve. And then in just general, like completely outside of data science. So when you say the letter frequency, you're saying that in the middle there where that line is, there's a group of letters that come up almost 50%. I've heard in English the letter S comes up a lot.
Well, yeah, I mean it's probably not 50%, but like we can see that like if I was able to label the axis, like some letter here is coming up, the most frequently, and another letter over here that is most likely the same letter is for this language is also coming up most frequently, and like somewhere up here is like the least frequent letter, and somewhere down here is.
Then I see the other dotted lines for the lines.
Exactly. Yeah. No problem. All right. Thanks, everybody.